Today we are going to talk about electric charge and electric field. For this, we will talk about Coulomb's law, the electric field calculated when we have continuous distribution of the charges. Then we go to electric dipole. Coulomb's law is an empirical law. This is what Charles de Coulomb Augustin did in 18th century. He did the experiment and then he verified it with this mathematical model. So he found out this formula. What reminds you this formula? Is the same thing as gravitational force. Do you remember when we studied force of interaction of gravitation between two masses is proportional to the product of masses and inversely proportional to the square of the distance between these two masses. The same thing here with Coulomb's law. If we have two charges distant from each other, let's say I have charge 1 here and charge 2 here, and there is a distance between them, and I call it L or R, just distance. And then this one I call it Q1 and this one Q2. The force of interaction using Coulomb's law is the same thing, is the product of the two charges, is proportional to the product of the two charges and inversely proportional to the square of the distance. K is the constant of proportionality and is given by 8.99 times 10 to 9 Newton meter squared per Coulomb squared. And also you need to remember this. 1 microcoulomb is 10 to negative 6 Coulomb, and this one also. Now let's clarify this. Now if I have two charges, let's say these two charges are positive. Let's say Q1 and Q2 are positive charges. Plus, this one has plus, this one has plus, and there is a distance between these two charges. We want to find the force between these two charges. You need to know if the two charges are positive, they will repel each other. The charges, they will repel each other. And the same thing, if they are negative, they will repel each other. If the two charges are opposite, one example is positive and other one is negative, they will attract each other. How we write these forces? If I'm studying this charge Q2, the charge Q2, it will receive a force from Q1. This is how we put it. We put the charge that receives the force, we put it in the front. The one that applies the force, we put it in the back. F21. Now, the force applied on this charge 1 from charge 2. Who receives the force is charge 1. Who applied is charge 2 in the back. The one that receives the force, we put it in the front. The one that applies the force, we put it in the back. Now, remember, these forces, they are linear on the line that passes by the charges all the time. So, you pass the line on the two charges and the force will be on that line. It can be repulsive or attractive. In this case, the force is pushing on the Q2 is pushing it, Q1 is pushing it away. Same thing, the force on Q1 is pushed in that direction because the sign is the same, it will push it away. Now here is the opposite. The force on Q1 from Q2 is Q1 will be pulled to Q2 and Q2 will be pulled also on Q1. When you study the charge, you look which charge are you studying. Then when you are studying that charge, look what is done to it. Don't look what does this charge. Look what is done to it. Let's go here and clarify this. Let's say I have this charge. Q1 is plus, because when you don't see negative sign, means the charge is positive. And Q2 is a positive. The question is to find the force applied on Q2 and the force applied on Q1 from Q2 and compare them. Then see the direction of each one of them. First, I'm studying Q2. Q2 has positive sign, then this is positive. I see what is done to it. I pass the line from the two charges. Then it has to be straight line. This Q2, it will be pushed by Q1. The force will be F21 in that direction. The same thing, this charge is positive. Now this Q2 is positive. You pass the line, and this one will be pushed in that direction. It will be F12. Now what will be their magnitude? How will we write the magnitude? The magnitude of this force F21, we put it between two brackets like that, and then it will be the magnitude of Q1 times the magnitude of Q2 divided by R squared. The magnitude R squared in this case is L squared because the distance is L in this case. Make sure the magnitude all the time is positive. The direction, it can be east, west, north, south, etc. The force F21 will be the same thing. K, Q, 2, Q1 in absolute value divided by the square of the distance. Did you see Q1 and Q2? They are identical charges in magnitude. Then the two forces in magnitude are identical. So when we write the magnitude, sometimes it takes too much time to write it like that. You just use F21 equal F12 without putting this bracket, means they are in magnitude identical. Just don't put a vector. Once you put vector, means you are including the direction. The conclusion, the magnitude of the force applied on each charge is identical in magnitude and opposite to each other. Now, what we need to remember also, Coulomb's law says that the force is proportional to the product of the charges and inversely proportional to the square of the distance. The constant of proportionality is K. I will let you do this example by yourself. We have Q1, which is negative 8 microcoulomb, Q2, 3 microcoulomb, Q3, negative 4 microcoulomb. Three charged particles are arranged in line as shown. Calculate the net electrostatic force on a particle 3. So if we want to calculate on particle 3, we need to circle this particle we are looking for. 3. Now, I don't look what 3 does. I will look what is done to it. How many charges around the charge 3? Q2 and Q1. Q2 is pulling. Q2, let me put it in red. Q2 is pulling to it. This is how I write it. Who receives the charge? 3. Who apply it? 2. Then I put it like that in red color. For Q1, what does to Q3? The two charges are negative. What will be? It will be, let it put it in blue. It will be a Y. I call it F. What F? It will be F3 because the 3 that receives the force from the charge 1. This is how we write it. Now, to calculate the net electrostatic force on the particle charge 3, we have two forces applied to it. We don't look what charge 3 does. We look what is done to it. So, and then we sum these forces. We calculate the magnitude of each force. We calculate, we find the directions, and then we add the vectors to each other. These two vectors, F32 and F31, are in the same line. Means we consider x-axis our reference. Anything that is east, we consider it positive. Anything that goes west is negative. We can do that, or if you take west is your positive or east is your negative, you have the choice. Now with this will not change about the magnitude and direction of the net force. We will show it on Q3. Now you calculate the net. Let's see. Now you calculate the net force using these two vectors we have. The net force is the sum of these two forces. I call it F net, which is F32 plus F31. You find the magnitude of F31. The magnitude has to be all the time positive. It will be the magnitude of Q3 times Q1 times Coulomb constant divided by the square of the distance between 3 and 1. In this case, the distance between 3 and 1 is 0.5 meters. 3 and 1 is 0.5 meters. You do the same thing for F32, which is Q3 Q2 times Coulomb constant divided by the square of the distance between 3 and 2. And the 3-2 distance will be 0.2 meters. If you replace this value, you get the magnitude of F31 and F32. Remember, F31 is going east. Anything that goes east, we consider it positive. In this case, we consider X positive is east and west is negative. But you have the choice, or you can call it right or left. So once you do your calculations, you will find the magnitude is 1.5 newtons in I add negative because it will be west. It will be 1.5 in west, 1.5 newton west direction. This is what will be the net force. Yeah, this is another example when we have multiple charges and they are in different positions, means they are no more on one line. In this case, we choose 3 charges, Q2, Q3, and Q1. Q2 and Q3 are on x-axis, Q3 and Q2 are on y-axis. So the question is, calculate the net electrostatic force on the charge Q3. So we do the same, we use the same principle. We circle the charge we are studying. We are studying Q3. We look what pulls and what push on Q3. So Q3 is positive. Let Q3, I put it here, is positive. Then Q1 is negative. Q2 is positive. Now just by looking to these things. Now what do you see here? This Q, what they do to it. Just look to Q3, what they do to it, these two charges. This one is positive, I'm sorry. Q2 is positive, Q3 positive, and Q1 is negative. Okay, what do you see? This one, let me move a little bit down. Q2, put Q2 here. Q1, put it here. So we can see the vectors nicely. Q1, I put it here. Okay, so what do we see here? We make straight line. Think it was a little bit off. Q2, I put it here, plus. What do we see? Q3, we just look what is done to it, because this is the one we study, Q3. Now what does to it? This one we're pushing it away. It will be F32. What does this one? Pulling it toward it. QF31. Clear? This is why you see these two vectors, F32 and F31. But now we can determine the resultant force F, which is the net force. How we do that? Very simple. We go, find the coordinate of each force, F31. Remember, we give these dimensions. We have 30 degrees here. We have 90 degrees here because it's perpendicular. And then we can find, if this is 30 degrees and I pass there, and this is my x-axis, When this is my y-axis, then I drop on x and I drop on y, and I get the coordinate of the force F31. It will be F31x and F31y. F31x, it will be F31 cosine 30 degrees, and F31y, it will be F31 sine of 30 degrees. Now, let me clean this and write them down there. We said F31 vector will be F31 in magnitude cosine of 30 degrees in x direction. Remember, when I drop here, it will be in y direction but south. It will be minus F31 sine of 30 degrees in y direction. Clear? This one east and south. The coordinate, you drop the vector on x and y axis. But for F32 will be just F32 in this case in y direction. All we need to do, we add these vectors. Remember to add y with y and x with x. This is why you see this force F. It will be has a coordinate on x and y axis. F net, we can write it like that, or just call it F, which is the total force applied on the charge 3. It will be F31 plus F32. We said F31, it was the F31 cosine of 30 degrees in x direction minus F31 sine of 30 degrees in y direction plus F32 in y direction. So this is F net. Now remember to add x with x and y with y. So we have this one stays by itself, F31 cosine of 30 degrees in x direction. Then I can put F32 in front because it's positive, minus F sine 30 degrees y direction. I put the coordinate that goes with y, I add them together. The coordinate that goes with x by themselves. So remember, this is a vector F net. Now, with the calculation, remember to find the magnitude of each vector. F31 will be the magnitude of Q3, Q1 times K over R31 squared. R31 means is the distance between the charge 3 and 1. The same thing, F32. It will be the charge Q3 absolute value times Q2 in absolute value times K divided by R32 squared. R32 is 0.3 meters. R31 is 0.6 meter, which is 60 centimeter. Then you do the math, you have the charges. Q3 is 65 microcoulomb, Q1 is negative 86 microcoulomb, and Q2 is 50 microcoulomb. Once you do the calculations, you should find F31 cosine of 30 degrees should be 120 newtons. And F32 minus F31 sine of 30 degrees will be 330 newtons minus 70 newtons will be 260 newtons. Your total force F, the magnitude of your force F, this is what will be. Then your F net should be 120 newtons x direction minus 260 newtons in y direction. Plus, I'm sorry, plus this is what will be your force F net. To find the magnitude of the net force F is F equals square root of 120 newtons squared plus 260 newton squared. It will be 290 newtons. Now, the magnitude of any vector. Let's say vector has 3 coordinates. Let's say this vector, I call it A, has AX in X direction plus EY in Y direction plus AZ in Z direction. The magnitude of this vector will be the square root of AX, AY squared plus AZ squared. To find the direction of vector F, you make a reference and identify the coordinate of force. Now remember the force F, it was 120 newtons in X direction plus 260 in Y direction. To represent this in reference X and Y axis, this is X and this is your Y axis. X axis is positive, 120, let's say, is in X. This is 120 newtons. And this is example 260 newtons. Now your vector F, it will be in the first quadrant. The angle, the direction is the angle that does your vector with X positive. This is X positive, and this is what we call the angle or the direction. The direction of F is a theta, which is the tangent inverse of Fy over Fx. Why? Because you go, this is your Fy, this is Fx, tangent of theta is Fy over Fx. We need the theta. To get the theta, you apply the tangent inverse to tangent theta, which is theta. Remember, tangent inverse of tangent of theta equals to theta. This is tangent of theta is Fy over Fx. The inverse of tangent of theta will be tangent inverse of Fy over Fx. Here will be the tangent inverse, or we call it arctangent, of 260 over 120, and this is 65 degrees. 65 degrees. This is what will be the angle that does the force F with x-axis. Now let's say we have an electric field E vector, and this electric field, for this electric field we are going to introduce an electric charge Q. Let's say we call it plus Q. So once we introduce an electric charge to this electric field, this charge will experience an electric force, and this electric force will be given by this formula, F equal Q times E. The direction of this electric force depends on the charge. Now let's say if I have a positive charge here, the electric force and electric field will be in the same direction. If I have a negative charge, the electric force will be in opposite direction of electric field. The direction of this force depends on the charge. If the charge is positive, it will be in the same direction as the electric field. If the charge is negative, it will be in the opposite direction of the electric field. The electric field due to point of charge. This point, we call it plus Q, has 1 microcoulomb, and we want to find the electric field at point P. The distance between Q and P, we call it R, is 1 meter. So by definition, the electric field given at this point P it will be the Coulomb constant times the charge divided by the square of the distance. This is the magnitude of electric field. The direction. To find the direction, you pass the line from the charge on point P, and the electric field will be away from the charge if the charge is positive. So this is what will be our direction of electric field at point P. So if it was the charge, it was negative. Let's say the same thing, and the charge Q, it was negative. To find the electric field at point P, you pass the line and you look to the charge. This is point P. The charge, the electric field will be toward the charge if the charge is negative. So this is what you need to remember. The direction of electric field depends on the charge. If I have point of the charge and I want to find the electric field at point M, I pass the line between the 2 points, and then the electric field will be away from the charge if the charge is positive, and toward the charge if the charge is negative. Constant K will be 1 over 4 pi epsilon 0, and 9 times 10 to 9 Newton meter squared divided by Coulomb squared. If I replace the Coulomb constant and the charge Q and the distance R, what will be my electric field? This is what will be our electric field. Remember, we said our electric force also will be the electric field times the charge. So the unit of the force is in newtons. The unit of electric field is newtons per coulomb. In this example, we are going to calculate the electric field at point P. At point P, and we have two charges. Q2 is 50 microcoulomb and Q1 is negative 25 microcoulomb. It's the same principle. We have point P, we have two charges, we will find two electric fields at this point P. So the sum of these two electric fields give us the net electric field. We call it E. Now E, which is the total electric field, it will be E1 plus E2. Now we need to find the directions of each one of them. This charge at this point. Now let's say this P, I just put it here. The charge Q2 is positive. That means the direction will be E2 will be toward west. Now for the charge Q1 is negative, it will be toward the charge Q1. E1 it will be in the direction of the charge Q. That means the two electric field will be west. The only thing we need to do is to find the magnitude. To find the magnitude is very simple. And find the electric field, it will be KQ1 times K R1 squared. Remember, in west direction we represented by negative x because we said x in that direction is positive. If we go west, it will be negative. The same thing, it will be plus K in absolute value Q2 times K times, I just put Q K there, divided by R2 squared in negative x direction because the two electric fields they are presented here, they are west. Now, once we do the calculations for each, remember we have Q1 is negative 25 microcoulomb, Q2 is 50 microcoulomb, R2 is 8 centimeter. 8 centimeter is 8 times 10 to negative 2 meters. Okay, let's say the same thing for 2 centimeter is 2 times 10 to negative 2 meters. Remember, the distances, they have to be in meters because we need Coulomb constant is Newton meter squared per Coulomb squared. So to find the force in newtons means this R1 and R2, they have to be in meters. So if we did the good calculations, we should find the total electric field E 6.3 times 10 to 5 in newtons per coulomb. The second question, we have to find the acceleration of this electron. Now what we did, after we found the electric field, we went and placed an electron. The electron has a charge, negative charge. The electron has negative charge. Remember the charge of electron. The charge of electron is negative 1.6 times 10 to negative 19 Coulomb. This is what will be the charge of your electron. And initially placed at this point P, then what it will be? If the charge under electric field, it will experience a force. We found the electric field E to be 6.3 times 10 to 8 newtons per coulomb, and it was in west direction. So west means it was in that direction. Now, when we placed an electron, this electron has a charge, negative charge, remember, which is negative 1.6 times 10 to negative 19 Coulomb. Now remember we said if we have a charge under an electric field, this charge will experience an electric force by definition. This electric force is given by the charge times electric field. The direction of this electric force will be in the same direction as the electric field if the charge is positive. It will be in the opposite direction if the charge is negative. Now in this case the electron is negative charge, the electric force will be eastward. That means if our electron is here, it will experience a force, and this force will be pushing it in that way. So in that direction, eastward. Now we need to find the acceleration. Do you remember when we studied Newton's law in physics 1025 and 2048? We said the net force applied on the object will be the mass of the object times its acceleration. In this case, we have electric force. This electric force is the charge times electric field. It will be the mass of the electron times its acceleration. The acceleration of electron will be the charge times the magnitude of electric field divided by the mass. Remember, this is the magnitude of the acceleration. Okay, so the direction of acceleration, remember the mass is scalar, is positive. The force direction will be identical to the direction of the acceleration. That means if the force is east, the acceleration also it will be east. That means once we place this electron in this electric field that goes west, the electron will be accelerating eastward in the opposite direction. He will go in that direction. Okay, so now the magnitude of this acceleration, we said the charge magnitude is 1.6 times 10 to negative 19 Coulomb times electric field will be 6.3 times 10 to 8 newtons per coulomb divided by the mass, which is 9.11 times 10 to negative 31 kilogram. Remember the Coulomb vanishes. Newton per kilograms is meter per second squared. So our acceleration, it will be 1.1 approximately times 10 to 20 newtons per kilograms, or 1.1 times 10 to 20 meter per second squared.